Stripping down science. The Naked Scientists.
Hello, it's Sunday, November the 28th, and a very warm welcome to The Naked Scientists with me, Chris Smith.
With me, Diana O'Carroll.
And I'm Dave Ansell.
Now this week, we're actually answering your science questions for you, including finding out what's more accurate, the speed of your GPS, or at least the speed it says you're travelling at, or your car's own speedometer. We'll find out how much does the Earth weigh, and how do scientists know that, and would an aeroplane full of birds weigh less if all the birds took off while the aeroplane was in midair? The answers to all of those are on the way, Diana.
Thanks, Chris. We'll also be hearing about a new technique to predict a person's age using just a drop of blood, and why frequent flyers might also be frequent forgetters. Jet lag affects your memory for up to a month, according to a new study that's just come out.
And in Kitchen Science, I'll be explaining why it's much harder to shake the contents of an unopened carton compared to one that's already been opened. Don't believe me? Grab a carton and give it a shake. I'll be back to explain what's going on later in the show.
I'm shaking my can and bottle here frenziedly, Dave, in anticipation. Thank you. If you've got any questions for us on this week's show, we'd love to hear from you. Tweet at Naked Scientists. You can write on our Facebook page. We've made it easy for you. You can get there by going to thenakedscientists.com/Facebook, and it will do the rest. Or you can drop us an email to chris@thenakedscientists.com.
The Naked Scientists podcast is powered by UK Fast, the UK's best hosting provider. On the web at ukfast.co.uk.
You're listening to The Naked Scientists with Chris Smith, with Diana O'Carroll and Dave Ansell. First up, let's take a look at some of this week's biggest scientific breakthroughs. Diana.
Yes, this week psychologists working at the University of Berkeley have found that jet lag affects the brain's ability to retain facts long after returning to a more regular schedule. The researchers came to this conclusion after they had subjected a group of female Syrian hamsters to 6-hour shifts in their circadian rhythms, which is the same as flying London to New York. They applied quite a tough regime to these hamsters, exposing them to this artificial jet lag twice a week for 4 weeks. They also kept a control group of hamsters whose schedules remained unchanged. Now, Lance Kriegsfeld and his colleagues then put both sets of hamsters through tests which measured their ability to learn and remember simple tasks, such as locating hidden food. Now, as expected, the jet-lagged hamsters didn't perform as well as the control group. But what was surprising is that the jet-lagged ones continued to perform poorly even a month after they returned to normal.
So that proves that it's not just being tired. There's something fundamental with memory going on.
Yes, there's actually something going on in the brain, and they found that the jet-lagged hamsters only had half the usual number of new neurons in the hippocampus area of the brain, which is really important for memory and learning. It's already known that frequent flyer humans and rotating night shift workers can suffer problems with their memory.
It's the shifts that rotate rather than the workers, yeah.
Round and round and round, that would cause problems, wouldn't it? But what this study implies is that those problems could persist even after they've settled into a more regular working pattern. But at least we know that this is true for hamsters anyway. But you can read more about that in the journal PLOS ONE.
Diana, thank you. Your boyfriend is a pilot, so can this be used to explain why he frequently forgets to bring you classy jewellery and all those wonderful gifts from exotic places that he flies to, like Luton?
That would be a very good excuse, wouldn't it? He's only short haul though, so I don't know if he'd get away with that.
Damn, I bet he's saying. Thank you. Well, also this week, scientists have come up with a way to work out how old someone is based on a blood sample. Now, previously, although genetic fingerprinting and other genetic techniques have made big leaps forward, largely thanks to the technique of genetic fingerprinting. For instance, we now know if you take a blood sample from somebody or you find a blood sample at a crime scene, whether someone has blue eyes or brown eyes, what colour hair they're likely to have, whether they're male or female, whether they have a tendency to male pattern baldness, for example, what their stature's likely to be like. You can predict all of those things from the genes, but the one thing you couldn't tell up until now was, well, how old is the person whose blood we've found? Because obviously ageing has an effect on all of those things. And now scientists have come up with a way that they say could get round this. This is Manfred Kayser. He's a researcher from the Erasmus Medical Centre in Rotterdam. And in the journal Current Biology this week, he and his colleagues have come up with a way to pinpoint, using just 5 nanograms of DNA, so a tiny amount, just a blood speck, basically, how old, plus or minus 9 years, a person is who left that blood sample behind. They did it by taking 195 healthy Dutch volunteers. These are individuals who are aged from just a few weeks old to more than 80 years old. And they studied white blood cells in the blood, because white blood cells, and specifically T cells, these are the white blood cells that fight off infections, these cells make inside themselves little tiny circles of DNA which they produce when the cells rearrange their DNA in order to fight off infections. But because, as we get older, the part of the body called the thymus that makes T cells gets smaller, you make fewer T cells as you get older, and therefore you have fewer of these cells making fewer of these little tiny circles of DNA. Those circles are actually called the SJ TREX, and we call them that because it's actually short for signal joint TCR excision circles, which is what these DNA pieces are. But what they do is to quantify how many of these little circles of DNA there are, and by plotting them on a graph, they could see that there is a linear decline with age in the numbers of these little DNA circles. And what they do is to take a gene which is present in only one single copy in a cell and use that to standardise how much DNA is there, and then compare it with the number of these DNA circles, and they can predict the age of a person based on this piece of blood. And they say that although that's interesting, and obviously it could be applied in things like criminal circumstances to work out the ages of victims or work out the ages of perpetrators, you could also use it in animals as well, because animals also make T cells. They also make these little circles of DNA called the SJ TREK DNA, and so you could use it for ecological studies. When you go and get blood samples from animals, you could work out how old they are, and this will inform our understanding of population dynamics.
So will different animals age like this at different rates?
Well, obviously we'd need to check exactly what sort of absolute numbers there are, but the point is you could do it in a standardised way, because the curve that they draw on their graph is a straight line, and this suggests that you ought to be able to say, right, if we know basically where along a curve someone is, it relates to this far along their lifespan, you could probably apply the same thing to the animal.
Brilliant. Now, scientists have managed to produce what's called a Bose-Einstein condensate of photons, so of light. Normally, if you call a gas or something similar of atoms, they keep existing in a variety of different energies, even if you get all the way down to absolute zero. But two scientists, Einstein and another scientist called Bose, predicted that if you cool certain types of atoms enough, they all start to condense into a single state, so all with exactly the same energy and exactly the same other properties, essentially behaving as one giant atom, and this is essentially a new state of matter. It was predicted in 1938, but it wasn't achieved until 1995, when Eric Cornell and Carl Wieman cooled a very low-pressure rubidium gas to about 170 billionths of a degree above absolute zero. So 170 billionths of a degree above the coldest temperature you can possibly get. And this formed a Bose-Einstein condensate, and they got a Nobel Prize for it just 2 years later. Now, if you used light, in theory, the same thing could happen, but at much higher temperatures. The problem is it's really hard to confine light. You've got a photon, it's moving at the speed of light, it's bouncing off the sides billions and billions of times every second.
But if you cool it down...
And it absorbs. And it's really difficult, so you can't keep it down, so it can't cool down. Now, Jan Claers and colleagues have got around this problem. They've trapped photons with 2 curved mirrors, which are very, very, very close together, so only like 3.5 wavelengths apart. This means that the photons can only exist in certain wavelengths, and the changes, the energy differences between these wavelengths aren't any which can be absorbed by the walls, so it's almost impossible for these photons to get absorbed.
So it just bounces backwards and forwards?
For a really relatively long time. They've put some dye molecules in there, so occasionally the light interacts with dye molecules and picks up the similar temperature to the dye molecules. So the differences between the photons get smaller and smaller and smaller down until the temperature which the dye molecules are at. And this actually works at room temperature, which is a really incredible thing.
But what can you do with it, and what does it prove?
First of all, it's a load of interesting physics, and lots of physicists will be saying, hey, lots of things to play with. But because all the photons will be exactly identical, you'll be able to produce very, very coherent, very, very narrow wavelength light, so essentially like laser light, but not laser light. And there are some frequencies which is really, really hard to make lasers at. So, and the high ultraviolet X-rays.
Gamma rays, for example.
Yeah, I mean, I don't know whether you actually get the two things close enough for gamma rays, but certainly up into the X-rays, you could build it by using these two mirrors and this mechanism, which opens up all sorts of lasers which we just can't make at the moment.
What could you do with an X-ray laser? The X-rays are pretty penetrating already, so what could you do with that? It'd be presumably very, very powerful.
Probably, it would only be powerful if you put enough energy into it. So, I mean, odds are you're not going to build one which is going to be able to knock down houses. The real thing is being able to measure things, because the shorter the wavelength, the more accurately you can measure distances. So you could probably take pictures of atoms. I mean, actually with light, you could take pictures of atoms. You could make smaller computer chips and things like that.
Brilliant. Thank you, Dave. Fascinating stuff. Now, Wednesday, December the 1st, is going to be World AIDS Day, and 2011 actually marks the 30th anniversary of the discovery of HIV, the agent that causes AIDS. So it's very timely that this week scientists have announced that they have solved one of the big outstanding questions that surrounds HIV infection, which is why the virus is so damaging to the immune system. Professor Warner Green is the director of the Gladstone Institute of Virology and Immunology at the University of California, San Francisco. He's with us now. Warner, hello, welcome to The Naked Scientists. First, can you give us a brief potted history of what actually happens during HIV infection? In other words, how does the virus get into cells and what's its life cycle?
Well, good evening, Chris. I'm happy to do that. And it's too bad that we're celebrating the 30th World AIDS Day, that we haven't ended this epidemic, but the number of new infections are, in fact, declining markedly throughout the world, which is very good news. In terms of the life cycle of HIV binds to the cell surface, microinjects its RNA genome into the cytoplasm of the cell, and then converts that RNA into DNA, a double-stranded version of the DNA, hence the name retrovirus, reverse flow of genetic information. The DNA is then integrated into our own chromosomes. The DNA is then expressed into new proteins and RNA, which is packaged into new virions, which bud from the cell and start the entire infection process over again.
And the cells that are targeted are white blood cells. They're CD4. They carry that marker on their surface, T cells, without which the immune system can't function properly. So one logical conclusion is the virus infects the very cells that orchestrate the immune response. So if you damage them, then the immune system is harmed.
Correct. Well, the real question is, how are these CD4 T cells dying? It was quite clear that the number of cells productively infected with HIV could not explain, in other words, direct killing could not explain the massive CD4 T cell loss that occurs during HIV infection. Then a theory was advanced that it's not the directly infected cells, but it's cells surrounding the infected cell, bystander cells that are dying. Our study now shows for the first time that, in fact, it is these bystander cells which are the principal cause of CD4 T cell loss, but they themselves are becoming infected, but in an abortive manner, an incomplete infection that arrests early after the virus begins the reverse transcription process.
How did you do this work? How did you prove that?
Well, the first key was to use a primary lymphoid tissue. We used tonsil. And in this tissue, we were then able to use each of the different types of new HIV drugs that interfere with precise steps in the viral life cycle. We were able to interrupt the life cycle with these drugs and ask whether or not CD4 T cell killing was blocked or not.
Ingenious. So by adding a different drug that works on a different aspect of the life cycle, you interrupt at that stage, see if the cell dies. If it doesn't die, that tells you that the effect that you're seeing, the bystander death in an infected patient, must lie downstream of that blockade. If the cell does die, it's upstream of where the drug works, and that confines the bit of the viral life cycle that must be doing the damage.
Right. We were able to narrow in the death window, as we called it, to a step during the reverse transcription process whereby the DNA is elongated into a chain longer than 150 base pairs. One of the real surprises in our study was it's not the virus that's causing the CD4 T cells to die, but rather it's the host cell's response to the occurrence or to the accumulation of cytoplasmic DNA in the cell cytoplasm. That's what triggers a defensive response in the cell. In an attempt to protect the host, the CD4 T cell commits suicide.
So this is something we've acquired through evolution to defend us against viral attack. Cells that sense this cytoplasmic DNA genetic material in the cell where it shouldn't be, tells the cell, I'm infected with a virus, I'll kill myself to protect the rest of the body. Unfortunately, when you've got the scale of infection going on like you have with HIV, this has deleterious effects then.
Right. And the other twist to the story that was a real surprise was that these cells do not die silently, but rather they are dying a fiery death with the release of what's called pyrotosis, which is the release of inflammatory cytokines. The entire cellular contents of the cell are dumped, which increases the inflammatory response. And we now know that there's a close relationship between HIV and inflammation, that these two go hand in hand, dictating disease progression.
And what is the implication of this, just to finish us up? Does this mean that we're now closer to understanding how to intervene in the viral life cycle better, so people who are infected with HIV don't lose all their immune cells in this way?
Well, one of the great milestones in modern medicine is the creation of a panoply of antiretroviral drugs, 26 FDA-approved drugs for HIV therapy at last count. All of these drugs can interfere with this death pathway. However, the new link to inflammation, and death with inflammation, now allows us to explore the possibility of removing that inflammatory component, which might allow the virus to grow in a non-pathogenic way. This might be important for certain clinical settings.
Let's hope so. Warner, thank you very much. That's Warner Green, who is Professor of Medicine, Microbiology and Immunology at the University of California, San Francisco. Diana.
It's fascinating stuff. Well, also this week, researchers in Massachusetts have discovered that the ability of our brains to determine whether a human face is male or female is affected by where in the field of view they appear. So, for example, a typically male face in the centre of our vision might be interpreted as a female face when it appears left of centre. In the real world, this isn't usually a problem because we have so many other cues about the gender of a face's owner, so features like hair, clothing and body shape can all contribute to our conclusions as to whether a person is male or female. So the researchers removed all of these extra cues and used computer-generated faces, which made a spectrum of very male to very female. And these faces were shown in random order to study participants, of which there are 11. Arash Afraz and colleagues ensured that each face was displayed for 50 milliseconds, not very long, and that the subjects kept their gaze fixed on the centre of the screen. Now, the subjects were asked to assign a gender to each face. And what they found was that while gender judgments were consistent for those faces in the centre of the visual field, those faces lying off-centre received different judgments. And the tendency of each subject to judge an off-centre face as male or female seemed to be specific to the subject. So what Afraz thinks this means is that it comes down to how our visual cortex is organised. Now, the visual cortex is the part of the brain that interprets images, and inside it, cells are grouped according to the part of the visual field that they interpret. So Afraz's conclusion is that the visual cortex has a limited number of neurons per visual field area that it uses to assign gender. So if the image is small and is interpreted by one part of the visual cortex, it can come to a different conclusion than another part might make. And that work is published in Current Biology.
That's fascinating. It reminds me of a paper we discussed that was published a couple of years ago, in which researchers did a similar experiment but asked people to assign gender to images of individuals coming towards them or away from them. And when the individual was coming towards them, people were more likely to rate the individual approaching them as male, and when they were going away, they were more likely to say, I think it's female. And from an evolutionary standpoint, you could argue that if a male is coming towards you, they might be more aggressive and therefore more likely to attack you. So it's better to make an error in terms of assigning male gender to an approaching adversary or potential adversary. In the case of a receding figure, that might be your mother who nurtures you wandering off, so you need to follow her. And that was the argument they gave. And it was about 2 years ago. But it's sort of similar, isn't it? It's sort of making sure you make the right accident in the right direction to defend yourself.
Yeah, but this is interesting because this didn't seem to give any evolutionary advantage at all, because people were only making the different decisions according to how their brains were organised as far as the research seems to show.
So what do you think the reason is then?
I have absolutely no idea, but it's interesting.
Dave?
Now, NASA has found a moon with a mostly oxygen atmosphere. Now, one of the unusual things about the Earth is, of course, it's got a lot of oxygen in its atmosphere, which isn't stable, and it's only there because plants keep producing it, so everyone's looking for planets with an oxygen atmosphere. The Cassini probe was orbiting Saturn, and it's discovered that the Saturn's moon's rear has an atmosphere which is 70% oxygen and 30% carbon dioxide. Unfortunately, this doesn't mean that Captain Kirk could beam down there and be comfortable in his polyester jumpsuit, and it doesn't indicate there's any life down there happily photosynthesizing. Rear's surface is made of water ice at minus 180 degrees centigrade, so Captain Kirk being a problem for a start, and it's getting irradiated by particles of solar wind trapped by the Saturn's magnetic field all the time. This breaks up water, releasing oxygen, which is then forming this atmosphere. There's also a bit of carbon dioxide being released, possibly from deeper within the moon as it gets warmed up by tidal effects or something. And whilst the atmosphere is about 100 kilometres thick, there's still only a few tonnes of oxygen spread out over the whole moon, which, if it was on Earth, would fill a reasonably large building. So it's incredibly tenuous, so Captain Kirk would be not in a good state either, because he'd just be running out of oxygen.
So are they arguing then we have to be careful when we're looking for oxygen because we've got very precise and accurate sampling measures, that there are other ways that oxygen could occur, and it might just be a misleading signal?
I mean, I think this one you certainly wouldn't pick up as a misleading signal, because for start, it's so tenuous you probably wouldn't even notice it if you weren't actually sitting. No one had noticed it up till now, and they only noticed it because the Cassini probe went really close. But there could be all sorts of other chemistry which we haven't even considered, which could confuse any idea of whether there's life out there already.
Life not as we know it then. Dave, thanks very much. So if you'd like to read up a bit more about anything that we've covered this week, the references, and there will be transcripts to all of those news stories that we've been discussing online, you can find them at thenakedscientist.com/news. This is The Naked Scientists with Chris Smith, with Diana O'Carroll, and with Dave Ansell. And stay there, Diana, because Oni, I think, wants to talk to you. Hello, Oni.
Hi, how you doing?
Very well, thank you. Where are you?
I'm in Phoenix, Arizona, in the United States. You guys' program is awesome.
Fantastic. Well, you can stay with us. That's brilliant. And you've, in fact, for saying that, we'll answer your question for you. Tell Diana what you'd like us to talk about for you.
Okay, it's kind of a three-part question. As some large snakes are able to swallow large animals, and I was wondering, is it true they could go months, if not a year, between meals? Also, if this is true, why does the food not spoil in the snake and get the snake sick, since it's such a large amount? And third of all, what happens to the bones of the food?
Okay, interesting question. Well, first of all, as far as I know, snakes can go, I think it's about a month between meals, or at least Burmese pythons tend to go about a month between meals. Some might go for even longer. But what they do is they will eat a huge, massive meal, maybe a rabbit, maybe something bigger. I think you've all seen the picture of the snake trying to eat the alligator. And they have special cells which can actually break down even the most complex parts of an animal, even their bone. There was a study a couple of years ago that found that snakes could actually digest bones of rabbits. They have cells which are shaped like golf tees which do this, which seem to be singular only to snakes. And also, I don't know if you've seen it, but there was some fantastic CT scan photography. It was put on the website of the BBC quite recently, which showed a rabbit actually travelling through a snake, and it took 130 hours for this rabbit to get digested. But in between meals, there's nothing inside the snake, so there's no food to go off.
Brilliant. Great to have you with us. Thank you for your question.
All right, thank you very much.
Take care. And thanks for that, Diana. Brilliant answer. A quick one here from David Munro, who is on Facebook, and he's written on our Facebook page at Naked Scientists, how is bone marrow turned to blood, and how is the marrow replaced once it's used up? Well, the answer is the bone marrow, which lives in the bone marrow cavity of bones. So if you cut across a bone and have a look, you'll see there's a sort of hole in the middle with lots of plates of bone which jut out into that hole. And those plates in healthy bone are covered in stem cells. And these stem cells are dividing very, very fast to produce new blood cells. In fact, the body destroys something like 10 to the 11 cells every single day and makes another 10 to the 11 cells every single day, and that's just red blood cells. In fact, we worked out over the course of a lifetime that you make 250,000 tonnes, a quarter of a tonne of new red blood cells over the course of a whole lifetime, so it's a very fast process. And these cells are just dividing all the time and pumping out daughter cells, which then slowly over a course of maturations turn themselves into the new blood cells. And this includes platelets as well. You have big cells called megakaryocytes, and those megakaryocytes bleb off little bits of their cytoplasm, the stuff inside the cell, which become these little bits that float around inside the blood, and they're what cause you to be able to clot. If you have a hole in a blood vessel, the platelet will stick on and it causes the blood to clot. And then you have white blood cells as well, lymphocytes. They're also made by stem cells in the bone marrow, which then go out from the bone marrow, go around the body and turn into mature immune cells. So that's how it works. Ben is on the phone. Hello, Ben.
Hi, Dr. Chris.
Hi, how are you?
I'm great. How about you?
I'm very good. Where are you?
Well, I'm calling you from Flushing, Michigan.
Terrific. Flushed with success we are. What can we do for you?
Well, I have a question for you that I think you might be able to help me out with. It's kind of a two-part, but you can pick which one you want to do, I guess. I was wondering what the weight of the Earth is, or the mass. Wondering if it's even possible to calculate how much Earth weighs or how much mass we have on this planet.
Okay, it's a good question, Ben. The stated weight, mass, we should say more accurately, of the Earth is about 6 times 10 to the 24 kilograms. In other words, if you turn that into tons, it's 6 with 21 zeros after it, tons. So pretty heavy. But the big question is, and this is where Dave can help me out, how do we actually know that something on the scale of the Earth that we can't physically put on a pair of scales, how do we know how much that weighs? Because Archimedes famously said, if you give me a lever long enough and somewhere far enough away to stand, I could lift up the Earth. But how would we have calculated how much the Earth actually weighs, Dave?
Well, the simple way of doing this is because anything with a mass affects everything around it due to gravity. You can, and if something's roughly spherically symmetrical, you can assume that all the mass is in the centre of the planet, and it behaves as if all the mass was right in the centre due to some neat bits of maths. And so basically what you have to do is, if you know how much gravitational force a kilogram of anything will apply to another kilogram of anything, and you know how much force a kilogram of substance is being attracted to the Earth, you know how big the Earth is, you can work out how much mass must be in the Earth. The second part of that is really easy. The working out how much force a kilogram produces is really difficult because it's about 10 to the minus 11 newtons at a metre for between 2 kilograms. And so it's incredibly tiny force, and it wasn't done until near the end of the 19th century. And you essentially do it with very, very large lead masses.
Henry
lots
Cavendish,
of pendulums.
was
Yep.
it? Did that?
Indeed. And then from that you can work out how heavy the Earth is, and from that how heavy everything else is in the universe, really.
Thank you very much, Dave. Diana, a quick one for you. Adam speculates, do head lice like dirty or clean hair more? Because we often hear it said when someone has a nit infestation, but they prefer clean hair. Is this true?
Yeah, that's what I like to think when I was a kid. Well, certainly...
Did you have them?
Maybe.
I never
my
did. I
school
feel
was
left
crawling with the things.
Lovely. Where did you go to school?
I blame the school. I couldn't possibly say.
I won't go there. It was a girls' school, so I think I'm probably okay.
Oh, no, primary school. Girls' school was, totally nit-free, honest. But anyway, back to the question. So the NHS claims that actually, head lice do prefer clean hair, but we were sort of talking about it earlier, and from an evolutionary perspective, it seems to make much more sense that lice might have developed and evolved with humans before they'd invented shampoo. So I think it's just as likely that they like dirty hair, and I'm sure there are lots of people with filthy hair that have lice in their hair as well. So.
Unless, of course, we're secreting something which kind of slows them down or makes them harder for their eggs to stick on the hair or something. And I don't know anything about this, but human hair oils might actually be quite good at kind of slowing down head lice.
And your argument would be if you wash the hair with shampoo, you actually wash away that natural protective effect, and the consequence of that would be that the nits would find it easier to infest you. Yeah. In other words, if you've got clean hair. And
purely because we've been living them for so long, it would make sense we'd evolved some way of discouraging them.
It's quite possible.
Very quickly, I have this one from Neil Denham, who is written to us on Twitter. If you would like to tweet at Naked Scientist, we'll pick your questions up. He says, I'm not sure how to phrase this, but in this very cold weather, by the way, it's -4 here in the UK for everyone listening on the internet and beyond these cold climes. He says, why do the male private parts shrink so much in the cold? And there is actually physiology behind this. It's not just people claiming this and making it up. It is true, honest. And the reason for this is that, in fact, the rate at which sperm is made in the testes occurs optimally at a temperature which is 1 degree below body temperature, so about 36 degrees, where normal body temperature is 37 degrees C. And that's why they dangle down in a little bag to keep them a little bit cooler than body temperature. Sperm actually can be stored and lives quite happily at a high temperature, and so that's why when the sperm's been made, it's moved up inside the body to structures called the seminal vesicles, where it's nourished and kept alive until it's needed. But the actual synthetic process occurs better at the lower temperature, and that's why the testes are dangling down. And you have supplying enveloping, wrapping around the testes in the scrotum, you have muscles called the cremaster muscles. And there's a reflex called the cremaster reflex, which shortens those muscles to bring the testes up closer to the body when they're cold, but also when you're scared, for obvious reasons, because terror can mean you have to run away or you might get booted somewhere sensitive. So you can elevate them. And so you bring them up closer to the body when you are cold, and you drop them down a bit when you are too hot to keep the temperature right for making sperm at the right rate. So that's why things tend to get a warmer blood flow closer to the body and therefore appear to shrink when it's cold, and they dangle down a bit further when it's a bit warmer. So there is some real sound science behind this. It's The Naked Scientists. It's Chris Smith, Dave Ansell and Diana O'Carroll.
Still to come, we answer more of your questions, and I've got a live kitchen science for you to try at home.
And just to revise what that kitchen science experiment is, people need to go and get a sealed packet or carton of some liquid or other.
Either that or a couple of jars and some water and some oil.
That hasn't been opened, critically. And
doesn't have, with the jars you can have empty jars or a full carton.
And give it a shake.
Yeah.
Diana.
Right, it's time for our planet Earth. In July this year, a fire devastated a Surrey beauty spot. Firefighters from 3 counties tackled the blaze on Frensham Common, but 86 acres of heathland were reduced to a scene of blackened devastation. It may take up to 5 years for the affected land to recover, but not everyone views fire as a destructive force. Planet Earth podcast presenter Sue Nelson joined paleobotanist Andrew Scott from the Royal Holloway University of London on the charcoaled remains of the blaze to find out how fire can also bring the past to life.
You can notice as we're walking, your sort of feet beginning to crunch, although it's a bit damp today. Lots and lots of different sizes of charcoal here.
Now, you've just put a trowel into the ground there. It almost looks like the sort of beautiful darkened compost peat that you might buy from a garden centre.
Yeah, and so you probably think, oh, this is terrible stuff. But in fact, this is preserving the plant material as charcoal. What I consider fire as is, if you like, a preservational mechanism for fossil plants. Because in many cases, this charcoal now is the cell walls have been converted to nearly pure carbon, and that material can get buried and survive for millions of years. Not only that, the anatomy of the plants are still preserved in the charcoal.
It's hard to see how anything could be preserved in what looks like the remains of a fire grate.
Yes, I know. It's sort of almost counterintuitive, isn't it? If you take this back, and we'll take it back to the lab and look under the microscope, you'll see that all of the different tissues of the plants are preserved. I'll collect a bag of the material so that you can actually see that I'm telling you the truth. One of the problems, of course, is that this material, as you commented, so who would think of collecting that stuff? And so one of the things we have to do is persuade people that this is incredible material. It tells us about not only that there was a fire here, but we can tell what was being burned.
A short drive away, and we're now in Andrew's offices. We've brought some of the charcoal with us, and you've got a microscope here.
So I'm just going to take some of this sample out.
A spoonful there, a bit like spooning out some tea, isn't it?
Sometimes they're often called fossil tea leaves, I think, for some people, anyway.
Oh, my goodness. You can see textures, almost like tiny seeds.
This is kind of all wet and clumped together, but one that I collected earlier and dried out. I think if I show you this under the microscope...
You're using a very fine-tipped paintbrush now to sort through the powdered charcoal.
Yeah. I'll just turn it round.
Oh, that looks like a clove in that, as much as it's got a little stick and a roundish head with 2 little pincer-like protrusions from the top.
That's a charred heather flower.
Gosh!
So let me find you another bit of the heather. This is another one of the flowers that's actually opened up.
That almost looks like a miniature black rosebud.
Yeah, It's amazing.
So the charcoal is a treasure trove as far as you're concerned, but why is it important to examine the remains of these plants?
Our thoughts about charcoalified flowers started with the discovery by Elsa Marie Fries and colleagues in Sweden of some Cretaceous material in which they discovered these tiny little flowers preserved as charcoal. This was a period when flowering plants first started. We know that many of the flowering plants were small, shrubby, weedy forms, and they survive well in disturbed habitats. But the other thing to know is that, of course, fire is a major disturbance. And if you've got regular fires, then these kind of weedy plants can do very well. They come back very quickly. If the fire return interval is quick enough, you prevent any trees growing. But the question is, why in the Cretaceous? And why is it so interesting? We know from experiments that if you have changes in atmospheric oxygen, that can affect fire. Because if atmospheric oxygen falls below 15%, you don't get fire, it gets put out. If you have much above the present level, you can begin to burn wetter and wetter plants. So the idea we had was that if you're looking ever wet environments, if you have increasing amounts of charcoal, it may indicate that oxygen levels are increasing. So we've just published our research which tries to use this as a proxy of atmospheric oxygen through time. Now, it turns out that the Cretaceous, this period of when flowering plants first got going, was a time of high oxygen. So we believe that there were many more fires that could burn. They promoted, if you like, the spread and diversification of early flowering plants.
Andrew Scott from Royal Holloway University of London, talking to Planet Earth podcast presenter Sue Nelson. There are links to a longer version of that interview, as well as the latest Planet Earth podcast, and they're at thenakedscientists.com/Planet Earth. Now, Chris, I've got a question for you. It's from Abby, and she says, what happens in your mouth when you use a straw, and how come you can still breathe?
Yeah, I mean, it's something we all just take for granted, isn't it? You put a straw in and suck up a drink or something. But what's actually happening? Well, the answer is that by changing the shape of your mouth, you're actually getting the atmosphere to do the work for you. So what you do, when the straw goes into your mouth, you close your lips around the straw, which seals off the outside world from the inside of your mouth. And you then change the shape of the inside of your mouth by lowering your tongue or drawing it towards the back of your mouth. And this is a bit like pulling the plunger out of a syringe. So you increase the volume inside your mouth, which means the pressure goes down, and it goes down so that the outside world has a higher pressure than the pressure in your mouth, and that pushes on the drink surface, pushing the drink up the straw and into your mouth. And the reason you can still breathe is because actually you're not breathing through your mouth, you're breathing through your nose, and the nasopharynx connects back into your throat, and that's not where this volume change is going on, because you've sealed off the back of your mouth with the back of your tongue. So you've got this closed cavity that you take the drink into, and then you push it down your throat in order to be able to swallow. So that's basically how a straw works. And it's not too dissimilar, really, to when you're getting oil out the ground, because when you've got an oil well, unless it's under high pressure, what you're doing is pumping something down into the well to push down on the oil and push it up above it, so the oil then gets displaced back up towards the surface. So that's how it works. Now, Dinah, while you're there, why don't you do this one? Ronan is on the line, and he's in Cape Town, actually. Hello, Ronan.
Hi there. I was playing around with some seashells that I got from overseas and a few seashells that I got from Cape Town myself here locally. And I noticed that mainly the ones that are with a spiral shape to them, if I hold them upside down, so I'm looking into the hole of the seashell, they all seem to spiral in the same direction, so that the opening of the shell would be on the right-hand side, and they all spiral inwards in that direction. I'm not sure which direction it is. And I was wondering why most of them, majority that I've got here, all of them, actually happen to spiral in that direction. Is there a reason for this, or do some shells spiral in the opposite direction?
Okay, good question. Well, it sounds like you've got a right-handed shell there, which is called a dextral shell. You do get other shells which are sort of left-handed, and they're more sinister, called the sinistral shells. But there's no real obvious reason why you get more right-handed shells right now than you do get left-handed shells. But many people think that if you have all shells within a certain population, which are the same sort of handedness, are all right-handed, it's much easier easier for them to mate with each other. So therefore, if you get one turning up that's left-handed, it's going to be difficult for the right-handed one to mate with it. But looking back over sort of paleontological records, you do get periods when more left-handed shells appear, and then you get periods when more right-handed shells appear, and it just seems to be something that fluctuates and changes with time. And at the moment, we're getting mostly right-handed shells.
Thank you, Ronan. Great question. Scott is with us. Hello, Scott.
Hello.
What would you like to talk about?
My son Andrew had a question, and it puzzled me. You know how kids have questions. He's 10 years old, and he was wondering how soap bubbles form. And I wasn't exactly sure. I figured it has something to do with surface tension, but it might not be the same mechanism as water surface tension with the polar bonds at all.
It's all interrelated with surface tension, but it doesn't work very well with pure water because a soap bubble is a very, very thin layer of water. And with normal water, the surface tension is so strong, it tends to be incredibly unstable, and it will just all form down into a droplet and pop the bubble before it's even really formed. But what you do to make a soap bubble is you add some kind of detergent, some kind of soap. These tend to have a head which really loves water and is very, very charged, and a tail which is very, very oily and doesn't like water at all. So they're very, very good for dissolving fats when you're doing your washing up, because all the tails stick in the fat. And so you have something like oil which doesn't mix with water, and then you surround it with lots of water-loving heads, so it's then soluble in water, and you can dissolve the fats and clean your washing up. But these also tend to stick on the surface, so all the water-hating tails tend to cover all the surface of water. And deeper inside the water, you tend to get kind of little vesicles, so little kind of spheres with all the tails pointing inwards and the water-loving heads surrounded on the outside. This means that if you increase the surface, just some of these vesicles kind of get pulled up to the surface, and so you can keep creating surface really, really easily. And they stabilise these very, very thin films of water, soap bubbles. And so, because you've got all this detergent in there, you get these great big thin films of water with a layer of soap on one side, and a little layer of water, then a layer of soap, which is really quite stable and will last a good couple of minutes.
Thank you very much, Dave. And wonderful fun, too. Mark Hampson says on Facebook, nakedscientist.com/Facebook, how does giant hogweed change skin and damage it? Giant hogweed produces a chemical which is actually used to treat psoriasis, people who have this skin condition psoriasis, and that chemical is psoralen. And psoralen gets in through the skin. In fact, if you take it into the body, it goes all around the body and goes into pretty much every cell in the body, but it's a photosensitizing agent, which means that a cell that's got it in can absorb light of certain wavelengths, and it produces a toxic chemical when it's interacting with light, and that toxic chemical can kill the cell. And so this is why, if you take it into your body or you get it into contact with your skin, the skin cells where the contact occurred become very photosensitive, and then when you go out into the open, there's enough ultraviolet light, just even at low levels on even a cloudy day, to interact with the drug that's in the skin and therefore damage cells in the skin, and it gives you an exaggerated sunburn. And that's actually an interesting phenomenon, because people, as I say, have now been able to take that out of nature and apply it to a medical condition, psoriasis, in order to get rid of some of the psoriasis lesions by putting people in basically a sunbed, and you dose of psoralen into the sunbed, and the rapidly dividing cells are more sensitive than normal cells, and so they tend to die off faster, and so that's how you treat your psoriasis.
Keeping you abreast of the world's best science, The Naked Scientists. For more information, look us up online at nakedscientists.com.
You're listening to The Naked Scientists with Chris Smith, with Dave Ansell and with Diana O'Carroll. And it's time now for our Kitchen Science, which has been inspired by Wink from Flagstaff in Australia.
I have an incredibly important liquid vacuum question. Well, about orange juice, actually. An unopened juice carton has liquid and a bit of vacuum at the top, but it's sluggish to shake. Crack the seal and let air in, and now it's noticeably easier to shake. Yet there's all this dense gas instead of vacuum. Exactly backwards to what I would think. What's up with this?
It's a very interesting question. Okay, so the first thing is, what's happening when you shake something to mix things up? I've got a jar, I'm doing this in jars so you can see what's going on inside. If I shake the jar, you can hear it's rattling around. The water, because water is a lot denser than air, if you accelerate it downwards very quickly, the water gets left behind and the air gets pushed to the bottom of the jar, and then when you stop, all the water flies downwards. And so you're getting lots of really violent movements because there's a big density difference between air and water. And so you're getting very, very violent movements. The water smashes into the bottom. Air isn't very viscous. And therefore you can get really, really rapid changes, very big shearing motions, so everything gets mixed in really well. So I was going to try and do an experiment to compare what happens if you have a very, very full jar and a half-full jar. And I'm attempting to mix oil and water, essentially make some rather unpleasant salad dressing. So I'm just going to pour a little bit of oil on the top of this jar, which is half full of water with a little bit of oil in the top. And I've got another one which I've very, very carefully filled right to the top with water and a little bit of oil at the top. So if I can get you, Diana, to give both of those one shake. So try and give them
one?
Just the one shake. A good,
How violent?
Just quite reasonably violent, but just the one shake.
Okay, right, this is the sort of half-empty one.
The lid is on, isn't it?
Yeah. Yep. Okay, so that's looking quite revolting. And now the mostly full one. That's looking a lot prettier. So what's happened? Why is the half-empty one looking so disgusting inside?
Well, the half-empty one, there's lots of space for the fluids to move around, so they bash into the bottom. As it tends to bash up asymmetrically, so you get lots of twisting motion, lots of vorticity, so everything gets spun round, lots of turbulence, and everything gets really well mixed. When you got the full one, the density difference between the oil and water is only about a tenth of that as water and air, so the forces are much smaller. Also, water's a lot more viscous than air, so all of the twisting motions are much, much weaker. They're not enough to break apart the surface tension of the water, so it hardly mixes at all.
And does the difference of the ability for the air to compress more than the water, does that make a difference?
I mean, that basically the air can get out of the way a lot quicker because it is a bit compressible. And in the carton, when he was talking about being a bit of vacuum at the top, of course, if there is any vacuum at the top of the carton, the air pressure on the outside will deform the carton immediately to take it up. So essentially, when the carton is absolutely full, there's no air space in there, so you've only got liquid moving around.
Terrific. Thank you both very much. And now you understand why it is so hard to shake the full carton when you get it out of the fridge. Lovely question from Robert and Billericay, who says, lying on the floor, revolver in one hand, rifle in the other, if you fire straight up in the air, will the bullets be harmful when they hit the ground? Presumably they're going to go up to a certain height and come down again. And the answer is, oh yes, they certainly will, because actually after Saddam Hussein pulled out of Kuwait, when he first invaded Kuwait, if you remember back at the first Gulf War, there were actually a number of people who got killed by people who went out on the streets and fired their guns straight up in the air, and the bullets that came back down again killed people. And you might think, well, why? They're just falling bullets. But the point is that the bullet is given a degree of energy by the gun, and that bullet will convert that energy as it goes up into the air into gravitational potential energy, and it will slow down in the process. But then it's got an enormous amount of potential energy. It will then fall back down to Earth, and there will be some losses because the bullet is interacting with the air, which will have frictional effects and slow it down a little bit. But at the same time, it will end up coming back to the ground because bullets are pretty streamlined. At almost the same speed, it left the gun. So it will come cannoning down into your head if you're underneath it. At the same speed it left the gun, you're effectively being shot, but from above. So very, very dangerous. Never do it. Right, Dave, you've got to answer this one. This fantastic question. Mark Zinner says, does an aeroplane transporting flying birds weigh less if they all take off?
Not very long. Basically, the birds are holding themselves up by pushing air downwards, and so as they push air downwards, they get an equal opposite reaction. They're held upwards. The problem is that air is going to keep on moving downwards until it hits something else. If you're in a plane, it will hit the bottom of the plane, and therefore that air will get slowed down and it'll transfer exactly the same force to the plane. So for the time it takes for the movement of air to get from the bird to the plane will weigh less. But as soon as the air hits the plane, then it will go back to what it weighed before.
Brilliant answer. Now, Diana, Leah, via email to chris@nakedscientist.com, if you want to send us a question, is wondering, did cavemen hunt and cave women cook? The stereotype is that prehistoric man went out and hunted and prehistoric women stayed in the cave and looked after the kids. But is there actually any archaeological evidence for this?
Well, the answer is we don't really know. It's something that paleontologists have argued over for years and years and years. But it all hangs around a thing called division of labour. And so the idea of that is you have certain groups of people doing certain types of jobs. And if you can divide people according to certain rules, say their gender or their age or something like that, then it might mean that they do a specific job. But of course, finding that in the archaeological record is actually really difficult, because you'd have to have a certain group of people fossilised along with the job they were doing, and you'd have to have it repeated over and over to show that it was happening in this society. So the answer is we don't really know what was happening all those years ago, because it's in prehistory. You can look at cave art, perhaps, but even then, how do you interpret some figures as male or female? Quite often the cave art isn't very easily identifiable in terms of gender. There was one theory that one guy came up with a few years ago who said that the Neanderthals actually became extinct because the women took part in hunting far too much and therefore were not able to bear children because they all got killed off.
Rather like the archaeologists and paleontologists who probably made that comment, who are probably blokes, I would think.
Oh, yeah, this was definitely a man who said this. But, I mean, it's certainly possible that women in Paleolithic times did take part in hunting. We don't know that they were busy making babies all the time. It looks like population was actually quite low, so who knows?
Can you compare it with modern kind of Stone Age peoples?
You get into trouble for calling them Stone Age. But yeah, I know what you mean. They do make comparisons. It's called ethnographic comparisons. So what you do is you look at hunter-gatherer groups in, say, South Africa or South America or in Papua New Guinea, and look at how they divide up their labour. And actually, it's quite a mixed picture. Sometimes you get very matriarchal societies where the women are in charge and the women go out and hunt and gather, and sometimes you get patrilineal societies and societies where the women stay at home and the men do the hunting. So it's, who knows?
Dave, got a really stinking question for you. Andrew Weissel says, if temperature is a measure of the average speed of molecules in a material, what is the temperature of a perfect vacuum?
Yeah, that is a very good question. It is often not very well defined. For something to have a temperature, it's got to have something in it to measure the temperature of. A perfect vacuum with no atoms, you can't measure the temperature of the atoms. So what's left in the vacuum, quite often there's light going through the vacuum, there's photons. There's very, very little, I don't know of anywhere in the universe where there's not really photons there. So you couldn't try and measure the temperature of the photons. The problem is quite often the photons don't have a well-defined temperature. They're not interacting with each other and sort of averaging out enough. So there'll be some very high, sometimes there'll be lots of very high energy photons, might be a load of X-ray photons and not very many microwave photons. So you can do it on the photons, but often it's not very well defined.
Well, that's a better answer than I could have given. Thank you very much, Dave. Des Emright says, hi there, and this is via Facebook, as was the previous question. How much farther can you see beyond the horizon as you go up each floor of a skyscraper? Well, let's assume your skyscraper is standing in isolation, so it's not going to get your view blocked by an adjacent building, for instance. So there's no get-out clauses like that. It's a building in isolation in the middle of nowhere. There's a sort of approximation for distance to the horizon, which is 1.23 times the square root of the height of your eyes above the ground in feet. So you could work out, using that little rule, how much further you're going to see if you go up the height in feet of one storey in a building, and then you could keep doing that to work out how much further you're going to be able to see to the horizon from the top of the building than the bottom, for example. Now, this one has created a little bit of contention on our forum, Dave, because we got this question that came in, and Andre Grobler got in touch about it. It was, how much more accurate is your GPS in your car for measuring how fast you're going than your speedometer? If you are driving along, should you rely on the average speed returned by the GPS as a better estimate of the velocity of your vehicle, or would it be better to take what the speedometer is saying as read?
Okay, the two devices are measuring speed in very different ways. The speedometer is measuring basically the number of times your wheels turn every second or every minute. and if you know the circumference of your wheels, you can work out how fast you're going. There can be errors on that because as your tyres wear down, that will change the circumference of your wheels. And quite often, I think they build speedos to possibly slightly underread, which is quite good because that way you get less speeding tickets. And especially because in old-fashioned speedos they weren't as accurate as modern ones. They weren't computerized, and they just tended to be less sensitive at high speeds. So they've actually kind of fudged that back into modern computerized speedos. So because people expect them to be less sensitive at high speeds, the GPS is basically measuring your position repeatedly and measuring how far you move over a certain period of time, and then dividing that distance by the time it's averaged over, and then that will give you a speed. If you're stationary, the GPS will quite often give you a speed, so the GPS is not at all accurate at giving a speed when you're going very, very slowly, because the errors in position can be a few metres, and the accuracy of the speed will depend how long it's averaging over to get the speed. So if it's averaging for 10 minutes, the GPS is probably more accurate. If it's averaging for 2 seconds, the speedo will certainly be.
So I'll stick to my GPS if I'm going too fast. No, I'm just joking. Don't rely on that in court, basically. Right, well, on the subject of really good questions, it's time for our question of the week. Diana.
That's right. This week, do you ever get that expanding feeling?
Hello, this is Father Jerry Drummond. I know that the universe is expanding at an ever-increasing rate, and eventually that will approach the speed of light. So what's going to happen then? Will it go faster than the speed of light? Presumably that's not possible. Will it stop? Will it start reversing and go back to a big crunch? Thanks so much.
And our cosmological model answer is...
So my name's Carolyn Crawford, and I'm at the Institute of Astronomy here at Cambridge University. Okay, well, the most straightforward part of that question is how fast the universe is expanding now, because this is something we actually measure. We call the current rate of expansion something called the Hubble constant, and that is really just a measure of how fast bits of the universe are moving away from us as a function of their distance. So as you go further out away from the Earth, bits of the universe are travelling ever faster. So, for example, if you go to 30 million light years away, maybe you've got a bit of universe receding away from us about 700 kilometres per second. Go 10 times further to 300 million light years away, it's receding at 7,000 kilometres per second. And if you carried on going further and further away, yes, you do get a point where you're far enough away and that bit of the universe is moving away from us at speeds greater than the speed of light. So it is not a fundamental speed limit. The key thing here to realise is that the expansion of the universe is caused by just stretching of space, and that can be at any speed it likes, much greater than the light speed. The thing that is constrained by the light speed is the rate that things can move through space. So the expansion of the universe is the stretching of space, and it's carrying the galaxies along for the ride. But any light, any signal information from those galaxies can't travel faster than the speed of light. So in fact, the expansion of space is not constrained by how fast it's moving, it's constrained by how much stuff is in it, and that's going to determine whether the universe will contract or carry on expanding forever.
If space objects are moving away from us at a speed faster than light, then the light from them cannot travel fast enough to reach us.
So all the evidence currently is that this expansion is getting ever faster and the universe is going to carry on expanding forever. So the speed at which it expands isn't affecting the eventual fate of the universe, but what it does affect is what we can see of that universe and how much of it we can see. Because if a galaxy is moving away from us faster than the speed of light, that means any photons of light leaving it can't travel across the space fast enough. It can't outrun the expansion of space. And so we have something called the observable horizon. So away from us, anything that's expanding further than the speed of light away from us will never see the light from those objects. And as the universe gets bigger and bigger, that horizon is going to shrink, and we're going to see less and less of the universe that goes on. And that's really what's going to be affected by this expansion speed.
But what about that crunch theory?
Whether or not the universe actually collapses back down on itself depends on how much matter there is in the universe and how much stuff there is to pull it back together under gravity. And really the current cosmological thinking is that with the presence of dark matter and dark energy, the universe is not going to contract. It's going to carry and expand. It's going to expand faster and faster and never go back to that big crunch at the end.
Current thought is the universe will just keep expanding. To sum up, objects are moving away from us in space as space stretches, meaning that they can travel away from us faster than the speed of light. But those objects cannot move through space faster than the speed of light. And our Clever Clogs forumer this week was Imat Phal, who got it all right. Next week, we've a rather basic question.
Hi, my name is Rob, and my question is, given that people can absorb medication in the form of suppositories, is it possible to absorb enough water to survive through their bottom?
What goes in might come out, but at which end? Answers to us by email with the address chris@thenakedscientists.com or write them on the forum, which can be found at thenakedscientists.com/forum.
You get all the bum questions, don't you, Diana?
Yeah, I do. I'm so lucky.
Thank you very much. Diana O'Carroll there with this week's Question of the Week. If you'd like to follow Question of the Week as a podcast in its own right, you can find it on our site at nakedscientist.com/QOTW or look it up on iTunes. That's it for this week. Next week, join us if you're interested in electricity for an electrifying show, because we're looking at new ways of generating power and distributing it in a much more efficient way. So if you have any questions about electricity generation and distribution, send them in to chris@thenakedscientist.com, put them on our Facebook page, Naked Scientists, or tweet them to @NakedScientists. In the meantime, let me say a very big thank you to all of our contributors this week, who were Warner Green, who joined us at the beginning to talk about his HIV work, to Dave Ansell and Diana O'Carroll, to our wonderful production team, Ben Valsler, Mira Senthilingam and Tom Simpkins. My name's Chris Smith. Have a great week and see you next time. Goodbye.
The Naked Scientists comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC, the Natural Environment Research Council and UK FAST. For more information, look us up online at nakedscientists.com.